Welcome, friends. So, let's discuss a new topic, cases of combined stresses. So, for that, first, what is the combined stresses? So, the combined stresses are the algebraic sum of the stresses. So, if we have the different stress like tensile stress or compression stress or some bending and the uh, shear stress, so the sum of all, either sum of two or more the stresses, we can say it is the combined stress. We may use the principle of superposition to sum the normal stresses means the axial stresses, that is the tensile or the compressive and bending. So you can say it's the axial stress, so the bending or the shear in that we can say it is torsion or the shear or torsion. So you may sum always by the principle of the superposition to sum up all these types of the stresses, so that is known as the combined stresses or the compound stress. So let us discuss the case 1. So the first case, tension and compression stress. Tension and the compression stresses. If the tension and the compression stresses acting along the same axis, so we can take simply the tensile stress as positive and the compressive stress as negative, then add them up, so we will get the combined stress or the resultant stress. So as for example, taken tensile stress, here we can consider, if on this we have an tensile stress 1000 newton, here is also 1000 newton, and uh, the area of this beam is, we can say, area that is 100 square, and this is the first tension stress. And one another component if we will take, so this is our compression stress on this. So here the direction of the stress is like this. So if it is of 2000 newton, okay, so here is the compression stress. So what will be the resultant of these two, so that we need to find out. So first we will find out the uh, what exactly the stress is there, so that can be calculated by the force applied per unit area. So that is what here in this case it is 1000 newton per 100. So as we will convert the units, then basically what we will get, the result will be, it's 10 megapascal. So this is the stress over there. Okay, so it is in positive because it is in tensile stress, so we may consider as positive. So in this case it is compressive, so we need to consider the negative sign. So for this particular case we can similarly we can find out the value of this as F upon A. So that is because it is a compressive stress, so we need to take the sign minus. So it's 2000 upon 100 again. So finally we will get the minus 20 megapascal. Okay, so the resultant will be, we will sum up these two. So that will be, because it is the larger value, so the resultant will be the compressive stress, and it will be simply, you can say, it's an compressive one. Okay, so this, it is of what, we will sum up these two, so it will be of 1000 Newton compressive stress. Okay, so here we can say, by this you will understand. So for this we have the direction of this tensile stress, so these are like this. So we are adding for this particular component and then this component. Okay, so this component can be understand like this. So here it is the compressive, so we are adding these two, this plus this, so resultant is this one. So what it is, it is simply the, like this, you can easily understand. So it is compressive one. Okay, it is what, it is of 10 megapascal, it is of minus 20 megapascal, and the resultant is minus 10 megapascal. So this is the resultant. Okay, thus the resultant is a compressive stress of 1000 Newton. Okay, so this is the case 1. So let's move towards the case 2, and let me raise this. So for the case 2, combining the bending and tension. Bending and tension stress. So when a beam is bent, it produces tension and the compression along the axis of the beam. So thus to understand this, let's say here it is a beam, and as in our earlier discussion, you know about the supports and the load which is applied. So these axial stresses can be algebraically added to the other tension and the compression. Okay, so here you may see that there is a tension and the compression stresses, so acting along the axis of the beam. So here this diagram of this can also be understood by like this, you can say, if this is our compression and this is the tension. Okay, so as we know, the sign for the compression it is taken as minus, and for the tension we will take the positive sign. So this figure shows at bending in the beam. Okay, so similarly for the tension in the beam, we will take some beam like this. If the tension is in this beam, so like tension in the beam only. So for this we can have this again, this structure, because there is only the tension in the beam, so we can have the structure like this. It is tension, so we will have the positive sign. Okay, and if we will add these bending and the tension stress, so the compound stress, the resultant for the compound stress, maybe let me draw it separately. So here it is the bending plus this is the tension stress. So if we will compound, we will get the combined stress of this bending and this tension stress. So it will be like this. So this is the our resultant stress in this direction. So this is the, this figure shows the bending and tension simultaneously in the beam. So this is our next case, second case. So let us take an problem based on this. So let me write down the question. So for this problem we need to calculate the maximum bending and the compression stress in the bracket. So for that so let load be splitted. This load can be splitted into the horizontal and the vertical components, that is for the compressive and the tensile stress respectively. So what it will be, it's I think it's 2000 uh, uh, cos 45 and 2000 sine 45. So finally as we will put the value, if this angle is given as 45 degree here, so let me draw this value will be, as you will put the value of cos 45 and the sine 45, so it will be equals to 1414 Newton similarly. Okay, 1414 Newton. Okay, so let me draw this figure again. So we are just we have uh, to let me draw the free body diagram for this structure. If this is our structure, so for that at this point a force of this 1414 Newton will be applied along this direction, and a force of again the 1414 Newton will be along this direction. Okay, and this distance is 300. So from this is, so we can find out the tension. So that can be equals to F upon A, and that is 1414 divided by 10 into 100. So the area of this 10 into 100 we can find out. So that is finally it's 1.41 megapascal. Okay, so for the beam, uh, the moment of inertia, if this beam is in rectangular, this is in rectangular one, so that for that we know the formula for the moment of inertia, that is I is equals bd cube upon 12. So we will put the values like it's b is 10 into 100 cube upon 12. So finally we will get the result of this calculation. It is 0.8 33 into 10 to the power 6. So the bending moment for this along this axis. So the distance is this, and the force is also I think 1414. So the value of this m can be calculated 1414 into 300. So this is our bending moment. So we know that in my previous lectures when we have derived the relation for the bending moment, so it is F by y is equals m upon I is equals z theta upon r, as you I think you remember about this. So for that we will use this first term. So the value of F can be written as it is m y upon I, and the y is also given. Okay, that is 50 here in this case. So we will put the values, and it is 1414 into 300, this value into y is 50 in this case, and it's 0.833 into 10 to the power So finally the value comes out, it's 25.46 megapascal. So this is the value of F that we have find out. Okay, so now the maximum tensile stress, maximum tensile stress can be calculated as it's 25.46 plus 1.41, so that is equals to 26.87 megapascal. Okay, and similarly the maximum compressive stress, so that is equals to minus 25.46 plus 1.41. Okay, so it is minus 24.05 megapascal. So like this we can find out the maximum values of the compressive stress and the tensile stress in this case. So for the next case, that is the combined shear and the tensile stress. Next case is for the combined shear and tensile stress. So as the information about the material strength is obtained from the tensile tests, in these tests only the pure tension in one dimension exists in the specimen. So however, in practice we do not have just only one direction tension. So in the components, we are not having one directional tension only. Okay, so there may be some bending, some shear, some tension. So consequently it is necessary to combine all these simultaneously acting stresses to get an equivalent stress to compare with the results of a tensile test. So for that we are assuming some by some figure. So I'm just trying to draw the typical belt driven shaft. Okay, so here I am just drawing a typical belt driven shaft. So if this shaft is here, I am just drawing this. So if these are the fixed bearing, here the shaft is fixed, and this is the pulley. Okay, so this shaft is subjected to torsion due to the power transmitted and to bending by the belt load. Okay, so this is for the pulley. Pulley causes bending load on shaft. Okay, and so for this what will be the rotation in this shear? So let me draw some diagram here. If like this we can say, so if this is the dia, and if this is the center, so we can say like this, and here it is like this. So here it is our shear stress, and here is the bending stress. This is the uh, bending stress, and in this direction shear stress. due to torque. Okay, so this figure B represents the bending and shear stress act in shaft. Okay, this is the another case, the next case for that. Okay, so for this okay, a more general case of the combined stress is when the component may be subjected to two normal stresses acting at the right angles plus the shear stress. Okay, so for the next case, let us we are having the these are the tensile or the normal stresses. So this is sigma x normal stress, sigma y again sigma y, and the shear stress along this direction, so it's tau xy. Along this direction it is tau xy. Along this direction it is tau yx. Along this direction it is tau yx. Okay, so as in the figure it is shown that the uh, components uh, may be subjected to the two normal stresses acting at the right angles plus the shear stresses as shown in the figure. Okay, so to analyze the maximum principal stress and the minimum principal stress or the maximum shear stress, so we have the we can add these as in our earlier discussion when the mode circle is discussed, and so then we can say the principal maximum principal stress. Maximum principal stress can be represented by uh, sigma 1, so that is sigma x plus sigma y by 2 plus it's a sigma x minus sigma y upon 2 whole square plus tau xy whole square. So this is our maximum principal stress, and the minimum principal stress, so that can be calculated by this formula again, the sigma x plus sigma y by 2 minus, so by using this formula we can find out the maximum or the minimum principal stresses. Okay, so for the maximum shear stress also can be calculated. So what will be the maximum shear stress? Let me raise this all. For the maximum shear stress, so it can be represented by tau maximum, so that is equals to sigma x minus sigma y by 2 whole square plus tau xy whole square. Okay, so like this we can find out the maximum principal stress, minimum principal stress, and the maximum shear stress also. So let us take an example. So in that these stresses acting on an object are given as sigma x is equals it's 20 megapascal and sigma y is 15 megapascal and tau xy is 5 megapascal. Okay, so you need to calculate the principal stress and the maximum shear stress. Okay, so it's quite easy. So you need to put the values of three variables given and you need to find out the sigma 1, sigma 2 and tau maximum. Okay, so I think no need to continue this. So it's quite easy problem based on this. So thank you, thanks for watching. For any suggestions you are free, if you feel, please feel free to write on my comment box also. Thank you.